Hi everyone. Today I want to practice with a classical experiment, race different object. Well, what I have here is a track and I can slide down this cart. Of course, in reality, friction keeps the cart from sliding down. But imagine that this is a really icy, oily surface. So there is no friction at all. To make it almost frictionless, these wheels let this cart move down practically like it would have been sliding. I also have a motion sensor connected to Logger Pro interface that is connected to a computer, so I can measure the position of this cart at different time. For that, a special software where it is right here. And then now I can make it visible for you. Now, let's check if it works. Okay, it takes data. And all I need to do is just let it roll while taking data. Okay, very good graph. At first it was not moving, resting. And this graph, this portion of the graph represents the motion. You can see that this line is actually a parabola. That means this is the motion with constant acceleration. And if I use a built-in feature of this software, I can try different fits. You can see the linear fit doesn't really work. The fitting line, the black one, should go along the red one, the actual graph. Well, that works nicely. So this is the equation, the motion equation for the car when it was sliding down. Now, what do I get from this? Well, this is the motion equation for the motion with a constant acceleration. And in this equation, if we look at the quadratic term, this term, it should be equal to this term. And the coefficient A as a unit of the acceleration. It is not acceleration, but it's related to acceleration. If we solve this equation, we get A equals A over 2. Hence, acceleration equals 2 times A. So acceleration will be equal to 2 times 0.4787 equals 0.96 meters per second squared. Now let's write it down. So what was happening? We had a cart kind of sliding down, and acceleration was 0.96 meters per second squared. Done with the cart. Now, instead of a cart, I want to roll down this sphere, and you can make a prediction. What do you expect with the acceleration of this sphere? Is it going to be equal to the acceleration of the cart, or higher or lower? And now we are ready for measuring. Okay, 1, 2, 3, go. Now, repeat the procedure we used for the cart and make an estimation for the acceleration of this sphere. So, same idea. The motion equation. We actually can extract the information about the initial velocity as well, but we don't need it. In this case, this coefficient should be equal to a half of acceleration. And this coefficient equals 0.3513. So acceleration will be equal to twice of that. 2 times 0.3513, 0.7 meters per second squared. So let's put it on the slide. So now, when you make it roll, the acceleration equals 0.7 meters per second squared. Naturally, 0.7 is less than 0.96. What does it mean? Why? Acceleration for the rolling sphere lower than acceleration for the sliding frictionless object cart. The reason is that the sphere rolls, and that is because there is a friction acting on this sphere. Without friction, the cart would have been sliding exactly like the sphere would have been sliding exactly like the cart. There would be no difference. However, because there's some friction, force of friction makes it roll, makes it rotate. That requires effort. For the cart, all we need to do to make it move is just let it slide, do it to force of gravity acting on it. However, for the sphere, it kind of slides and rotates at the same time. There is a very important physical quantity called inertia. Inertia basically represents an ability to resist the change. And higher inertia means it's harder to change the state of an object. In this situation, by the state of an object, we mean velocity of an object, velocity of the middle point of an object. For the cart, acceleration changes velocity, and velocity changes from 0 to like 1 millimeter per second, then from 1 millimeter per second to 2 millimeters per second, then from 2 to 3 millimeters per second. That's what we call speeding up. It takes a certain amount of time to make that change from 1 millimeter per second to 2 millimeters per second, from 2 millimeters per second to 3 millimeters per second, etc., etc. And for the sphere, when it rolls down, of course, velocity of the middle point changes from 0 to 1 millimeter per second, from 1 to 2 millimeters per second, from 2 to 3, etc. But for the sphere, it takes more time. And that's what inertia means. It takes more time. It is harder to change the velocity of a sphere than change velocity of the sliding cart. Why? Well, precisely because we need to make it move, plus we also need to make it rotate. That requires more effort, so the rolling sphere is more inertial than a sliding cart. We just proved it by calculating the accelerations. Again, for the sphere, it's lower than for the sliding cart. And now, if I ask you, if we let them roll together at the same time, move together at the same time, then which object gonna win this race? And the answer is now obvious. The object with less inertia should use less time to travel the same distance than the object with more inertia. So since the sphere has more inertia, it will lose the race. I'm gonna change the setting. Okay, let's remove this student who came here while I was setting this up. Stay there. And now let's check the theory. Let's make them race. The cart, the sphere. So now we know that since the sphere has more inertia, it should take more time for this object to travel same distance. So if we let them move simultaneously at the same time, then the cart should win this race. We should look at the center of each object. So when I let them go at the same time, let's see what's going to happen. 1, 2, 3, go. So you saw the sphere lost the race. Now let's do the classical experiment when we're going to roll down 3 shapes. A hoop, also called a ring, could have been a hollow cylinder, a disc, and a sphere. We don't know, we have no theoretical prediction about the inertia of each object. If we knew which has more inertia, which has less inertia, in that case, we could have made a prediction which one going to win the race, which one going to lose the race. But in this case, we're going to do the experiment backwards. We're going to let them roll, and based on the results of this experiment, we will make a conclusion about the inertia of each object. That's it. This is one of those situations when I wish I had a third, and it happens a lot actually when you teach on a count of three. 1, 2, 3. You saw that the sphere wins this race and the ring loses. So what does it mean? It means sphere has the least amount of inertia and the ring has the most amount of inertia. Why? Well, that's a completely different story. That's for a different video. A nice experiment when we can roll down different shapes, but you can take a look at a neat application that demonstrates what's going to happen. You can see that in this experiment, the sliding down cart wins the race over the rolling down sphere. Let's see a different experiment. And from this experiment, we can make a conclusion about the inertia of these objects. So these three objects roll down, take different time to achieve the finish line. Bye, everyone.